All right, plane geometry, chapter 1.18, constructing a perpendicular bisector of a line segment. But before we get too far into that, I want to go over page 30 in your book. Talks about geometry and the pyramids, and this is how I got interested in math, because I told you before I hated math when I was in high school. I wasn't any good at it. But when I had to take a history of math class, that's where it became really interesting, because I never thought about how much it took to get us to where we are, and how much I struggled with learning math. And I had a book, and I had a teacher, computers were coming around, internet was coming around, and becoming more popular. Cell phones didn't exist then, but we look at today, we have cell phones and these crazy calculators that do so much for us, and all the tools that we need to help make math easier, and we still struggle with it. But they, the people that discovered math and have used math for a long time were basically drawing in the sand, working off a candlelight, and didn't have the stuff that we have today. Page 30 kind of touches on that. It talks about geometry and the pyramids. So the first thing is the Egyptians, they didn't worship God and have all the, the way he created the world, but on all his mathematic principles and such. They didn't worship him. They didn't study math like some of the other people have studied it. They just had to survive, and they built these pyramids that are incredible. Let's just look at part of it. So the Egyptians contributed a lot to geometry, as you can imagine, because to build a pyramid is very geometric. The first thing that stands out to me is, if you look, it's talking about the Great Pyramid of, and I don't know how to pronounce it, we'll say Khufu, is probably completely wrong, but it was built around 2650 BC, so 2650 years before Christ walked the earth, and they were already using geometry unknowingly. They didn't call it geometry, but they were already using it in order to build these pyramids. So it's a man-made stone mountain tomb that's 481 feet high, and for us that's equivalent to a building that is 40 stories tall. They didn't have cranes and forklifts and any of that modern equipment to do this. They did all this by hand. That's incredible to me. It measured 755 feet at each of the 4 bases and covered a 13-acre plot of grounds. That's 8 football fields. And 40 stories tall that they built this pyramid. To do that, they had to start with level ground. They had to start to have something level to build this pyramid on. And again, they didn't have levels like we have today. They didn't have all the laser levels and the heavy equipment to move dirt. They just had to do all this by hand. And the way that they determined whether it was level or not is they took a piece of string and tied it between 2 sticks. And they took each one of those sticks to a body of water and touched the top of the water, because water levels out on its own. You don't have to have a tool to determine if water is level. Unmoving water is level. And they used that to determine what level was, and then they leveled out the ground. Just that would have been a task in itself. 8 football fields worth of ground that they leveled out by hand with no heavy equipment. Out of 30 million cubic feet of limestone, they excavated these big building blocks. Then they used inclined planes to move the stones, and they weighed as much as 2.5 tons, 5,000 pounds. Again, no dump trucks, no bulldozers, no forklifts, and they had to use over 2,300,000 stones to complete this pyramid. Since then, now that we do have modern equipment, we have things to see how precise they were. We've measured, and they found that the southeast corner of the pyramid stands only a ½ inch higher than the northwest corner. A ½ inch difference over the length of 8 football fields, or 755 feet bases, and they only lost ½ an inch of being perfectly level. Is incredible. The 4 faces of the pyramid form nearly equilateral triangles, so each side of the pyramid is almost a perfectly equilateral triangle. Didn't have the tools we have today to do that. that they all have an angle of 51 degrees 52 minutes with the ground. The right angles of the corners of the 13-acre square base are equally precise. The largest single error is less than 1/20th of a degree. That's pretty incredible, because all they could do is look at it and use archaic tools to be able to build this. And if that, you don't have to be good at math to appreciate how much of it is around us and how much it's been used to get us to where we are today, and how incredible it was that these people that, in our minds, we think of these historic figures as almost Neanderthals or cavemen, or not very smart, and they were doing things that most of us today wouldn't be able to do without the tools that we have to be able to do it with. So that's just a little bit in the book that hopefully will pique your interest a little bit, and maybe give you a better idea of why it's important that we keep carrying this math along. We look at it and say, why do we need math? When are we ever going to use it? Well, you never know. You never know when we'll need to use it, but it's all around us, and that just shows an example of how long it's been used to do the things that we do today. All right, let's get started. 1.18, constructing a perpendicular bisector of a line segment. A perpendicular bisector, we've talked about it. A perpendicular bisector is going to bisect a line right in the middle. It's going to be perpendicular, so it's going to come off at a 90 degree, so if I have a straight line. All right, if I was to just say, I think the middle of this line is somewhere right about here, and then I'm going to make another straight line, and I'm going to cut through it. And then I say, well, that's equal to this, and that's a 90 degree angle. That's the idea, but we want to be more precise than that. To the naked eye, maybe that does look like a perpendicular bisector, and maybe I got lucky and just happened to hit dead center on that line and made a perfectly perpendicular line to it. Chances are, though, it's not that accurate, and if we want to be anything like those Egyptians we talked about, to where we're only a 1/4 inch off at 8 football fields worth of length, then we're going to have to do better than just guessing. All right, so the way we're going to do that is we've got a straight line. Now, what I want to do is construct. We've talked about constructions. I want to construct a, I'm going to have to do a shorter line because I don't have a big protractor yet. So I'll make a shorter line, and I want to make a perpendicular bisector using a compass. And the way I'm going to do that is I want to use my compass in a way that reaches further than the halfway point. So I don't know exactly where halfway is, but I do know that I'm beyond. I'll even go a little bit further. It doesn't matter where I go, this is still going to work. So I'm going to go above it, and then I'm going to come up, and I'm going to create an arc length here, and then I'm going to do the same thing down here. Now, once I get a bigger compass, this will be a whole lot easier to show you. All right, then I'm going to do the same thing from the other side. All right, so I'm going to get on this end and do the exact same thing and do it on the bottom. All right, and what I see is I didn't go far enough on this bottom one, so I'm going to come back to this side and extend it. Again, it would be way easier. It would be easier on your paper than it is on this dry erase board. Okay, so I've got a straight line, and I've made 2 arc lengths from either end. Basically, on my compass, I used the endpoint. We'll call this endpoint A and this endpoint B. And I used my compass to go beyond the midpoint of this line and make my 2 arc lengths. I could have done them up higher. I could have stretched it out as far as it would, and it would have been further, but that intersection still would have been in line, okay? So now I'm going to take my straight edge, and I'm going to take the intersections of those 2, and I'm going to draw a line right through the middle of them. And now I've created a perpendicular bisector. So if I put my compass on this, I see that I am 90 degrees. So I've got a right triangle, or a right angle, 90 degrees, got a right angle, so everything is right angles. These two lines are perpendicular, and this vertical line is exactly the bisector of line AB. So this side of it is 3 inches, and this side of it is 3 inches as well. So I've got 3 inches on both sides where I split it right in the middle, and I did so without using any measuring tools. I didn't use, to construct it, I didn't use a ruler to find the center. I just used a compass, made my marks, found the intersections, and made my vertical line between them, creating or constructing a perpendicular bisector. All right, that'll give you exercises 1.18, questions 1 through 7. And that'll get you some practice with constructing a perpendicular bisector.